Hello, Prof. Teo. We are Group 2 from Seminar 6, consisting of Junhong, Joshua, Zhengjie, Yizhe, and I. COVID-19 has generated tons of data about countries and vaccines from different datasets. And this makes it important for us to contain such data in a database. We utilize two such tools, MySQL and MongoDB, in our attempts to model this data. And this will be our presentation table of contents for today. We will first discuss our relational database design and its SQL queries, followed by our non-relational database design and its NoSQL queries. Finally, we will conclude with our recommendations to the World Health Organization on which design is better in the context of COVID-19 data. Firstly, let's take a look at our entity relationship diagram for relational databases. Our ERD is pictured as such and consists of 11 entities, highlighted as such. Let's first take a look at the relation between location and vaccine. In the original dataset, it is mapped in country vaccinations by manufacturer as shown on the left, and as a multi-value attribute in country vaccinations. To get to the first normal form, this vaccine attribute must be changed since no multi-value attributes are allowed. However, we simply cannot drop this attribute since not all relations between country and vaccine, such as the one on the right, exists in country vaccinations by manufacturer. Hence, this relation between location and vaccine in country vaccinations must be decomposed. Since they share a many-to-many relationship, we decompose it into a weak entity. And this is implemented via an intersection table. Next, we observe that the primary key in all three datasets is a composite key of location and date. But the location attributes in COVID-19 data depend fully and only on the location. This is a partial dependency and must be removed to get to the second normal form. We do this by creating a new location entity and shifting all location-related attributes into that entity. Location then becomes a foreign key in the original datasets. With the second normal form achieved, we also observe that ISO code and country are both candidate keys. Location attributes can be derived from ISO code, and ISO code can be derived from country. This creates a transitive dependency and hence requires us to separate ISO code and country by creating a new ISO code entity as shown. Lastly, due to the nature of data collection, certain attributes can be grouped together to decrease entity size and reduce the number of nulls in the database. We hence split COVID-19 data and country vaccinations into the following entities: stringency, vaccinations, hospitals, cases, tests, and deaths. Hence, this is our final ERD, representing the original three data sources in a database that is in third normal form. The SQL scripts to perform this normalization, as well as the database dump ready for import, can be found together with this submission. During the implementation of this database, we also clean the data by replacing empty strings representing missing information with nulls and coercing columns to use the correct data types. This is to reduce query complexity and development time by simplifying the query. Next, Zhengjie will be presenting on our SQL queries.
Thank you, Brian. After implementing our relational database, we can carry out queries to gain insights from our data. We carried out many queries that can be found in the appendix of our report. Thus, I will just go through a few important insights that we found. We will first look at question 3, where we will generate a list of unique data sources. From this question, if we use the source name as instructed in the question, we are unable to get the correct answer as there are multiple countries with the same source name. One example is that Ministry of Health is found for countries such as Argentina, Australia, Uganda, and more. Hence, we took this into consideration when implementing our database. Thus, all we need to do is to use distinct to find the distinct source names from location table, as it depends on country instead of purely on source names. After which, we need to filter out source names that are null, since sources is left joined with location in our implementation. In this question, we use distinct, which is useful when we are trying to find unique sources or data. Overall, this will be helpful for WHO to find quality and quantity of data sources available. Next, we will now look at question 9, where we will be finding the vaccination drivers. To illustrate this, we decided to find vaccination for each available vaccines after 20, 30, and 40 days, based on daily new cases for Germany. Firstly, we generated the date for 20, 30, and 40 days later by using the function dateAdd. Next, we will extract new cases, vaccines, and total vaccination from each date in our cases table by joining our case table with our country vaccination by manufacturer table on location and date. We will also filter our rows to only include data where location is equal to Germany. After which, we will get the table as shown below. Next, we left join the date generated with country vaccination by manufacturer to get the total vaccination that is available 20, 30, and 40 days later. Finally, we will be able to get the final table with the new cases for each date and the vaccines available 20, 30, and 40 days later. With this, WHO can apply the same method to find vaccination drivers for different countries around the world and analyze how the number of new cases will affect the available vaccines in the future. With that, I conclude our portion on relational database design. Now, I will pass my time to Joshua, who will be going through our non-relational database design. Thank you.
Thank you, Zhengzhe. Moving on, databases can exist in many forms, each with their own benefits. Allow me to elaborate more on our non-relational database design. For a non-relational database, we use MongoDB, which can store humongous amount of data in a non-tabular form. Such a database is document-oriented. Unlike rigid scheme structures like MySQL, MongoDB allows users to have the flexibility to alter their data model based on their business needs. One can easily add new fields to the collections, making the NoSQL dynamic. This is highly applicable to storing COVID-19 data, where the data changes every day. So what exactly are the benefits of NoSQL? Firstly, it allows high scalability and high performance. NoSQL databases uses sharding to partition data on multiple machines, allowing organizations to have the right data in the right place at the right time. Next, NoSQL has high flexibility for users. As data grows, non-relational databases can expand to another device and shrink if things slow down. In implementing our database design, we first had to clean our data. The raw data set presents all the data in strings. Thus, we had to convert them to their specific data types, in, double, and date respectively. Most importantly, converting date into a string requires special attention. Date is stored in different formats in different databases. Hence, there is a need to reformat the string before converting it into a date data type. This is because using a slash delimiter is a non-ISO format. As such, the string will be passed into a date of a local time zone, which may result in the date being passed into an incorrect day. Thus, we had to ensure that the string is hyphen separated before converting it into the appropriate date data type to ensure passing accuracy. Lastly, we are presented with some data inconsistencies. For example, total vaccinations amount differs for all three collections. We attribute the difference of around 0.2% to human error. After cleaning the data, we can proceed to merge our collections. Generally, storage is allocated at the database level. Hence, multiple databases will consume more space than a single database with multiple collections. COVID-19 data will only grow continuously. Thus, we need to store data in a way which allows extensibility. By merging into a single collection, we can easily partition the data and take advantage of MongoDB's auto-sharding feature to distribute the data. This allows data storage optimization, which is central to many organizations. By merging the collections into a single collection, we can improve the speed of querying. This is because the lookup function in NoSQL performs significantly worse than joins in MySQL. In addition, minor changes in data or aggregation requirements may require changes to application logic. Thus, combining the collections into a single collection makes it easier for users to change their query based on organizational needs. Hence, we decided to combine the country vaccinations by manufacturers and COVID-19 dataset, which requires a lot of cross queries by reducing query time using less lookups. However, we decided to leave the country vaccination datasets as a standalone collection, as it does not require the joining with other collections for queries. In addition, merging this dataset with the other two datasets will make the dataset too big, which requires more advanced concepts like sharding. Next, I will pass my time to Ita, who will elaborate more on the queries.
Thank you, Joshua. Now I'll be going through the queries our group has done based on the merged dataset. The first query would be, what are the countries that have fully vaccinated more than 60% of its people? To tackle this query, our group used the aggregate function, which can be used to tackle more complex queries. We split it into 4 stages: the group, match, project, and also sort. In the group stage, we grouped them by their countries and sieved out vaccines and also the vaccination percentage using the max function. We then matched this to greater than 60. So we matched and found vaccination percentage more than 60, and this will return all records for vaccination percentage more than 60. Next, we projected country, vaccines, and also vaccination percentage, as this is what we were interested to find. And last but not least, we sorted them in descending order by setting vaccination percentage to -1. And as you can see below, this is our results of the query. If you haven't noticed, the country Gibraltar has a very high vaccination percentage and is in fact over 100%. Our group has done a quick check and we found that this is actually not an error. This high vaccination percentage can be due to the inclusion of foreign workers who were vaccinated in their country. And as a result, this vaccination percentage went over 100. Moving on to the next query is something closer, much closer to home. The query asks us for when is the first batch of vaccinations recorded in Singapore. In this query, our group used the N aggregation function to find records for Singapore and also daily vaccinations more than 0. Thereafter, we projected the date clean, as this is what we are interested in. And we also use the limit function, which limits the number of records shown. However, we can also use the min date to just project one date. During this query, our group realized that if we had used total vaccination greater than 0, we would get the date 11th January instead. However, after much discussion, we have decided to use daily vaccinations clean, as we decided that it's more reliable. We can see that total vaccinations can be calculated from taking the previous day's total vaccination plus today's daily vaccination. So 3,400 plus 2,800 gives us 6,200. Hence, we find daily vaccination to be more reliable, and hence we use daily vaccinations in this query. After finding this date, we brought it over to the next query, which asks us, based on the date identified specific to Singapore, compute the total number of new cases thereafter. Once again, we use the aggregate function where we match, group, and also project. First, we match location Singapore, and we also use match the date we have found just now. This time we did not use the AND function, but with 2 matches in a row, it serves the same purpose as the AND function. We then grouped them and also projected the number of new cases thereafter. So the number of new cases we found was 3,688. Moving on, Jin Hong will talk about one more query and the recommendations to WHO. Thank you.
Hi, I'm Jun Hong, and I will be covering the last query for NoSQL. So for question 13, the question asks us to generate a list of unique data sources, which in other words means generating the unique source names. What we do is we make use of the add to set operator, which adds a value to an array if the value is absent. If the value is already present in the array, nothing is done. This will ensure only unique results are added to the array. Then we just project the array to get the results as shown in the slides, and the results will be in an array. So now I'll be moving on to the final part of this presentation, which is our recommendations to WHO. So after considering all factors, the pros and cons of both databases, we came up with a conclusion. We recommend WHO to use NoSQL as we feel it is more suited in this scenario. We will be explaining more in the following slides. And before that, let's make a comparison before the two database models. Firstly, relational database has a rigid schema, which means that columns have to be defined before data can be added. On the other hand, non-relational database is more dynamic in nature, which means that new information can be added easily, and some data can have more fields than others. Next, relational database store their data in rows and columns, while non-relational database use a JSON format. Relational databases are also usually difficult to scale, while non-relational databases are easy to scale. Because of the relational nature of relational databases, it is more suitable for interconnected data. As for non-relational databases, since they are more dynamic in nature, they are more suited for unstructured data. And finally, relational databases usually requires normalization, while non-relational databases have collections that can often be combined into one. Having that, we can now justify why we chose NoSQL. Firstly, our dataset has lots of nulls and empty values, which will show up in relational databases. Non-relational databases tend to handle null values better, as the fields will simply be omitted. Secondly, relational databases are too rigid, and our data has a variety of columns. Non-relational databases are dynamic in nature, which is much preferred with this type of data. Thirdly, after normalization, we have 11 tables in our relational database as compared to 2 collections in our relational database from combining. As such, it is much easier to query from 2 collections as compared to 11 tables. There will be lots of joins resulted from the relational databases. Lastly, since COVID-19 is relatively new, we expect more data to be collected in the future, with more variation in terms of fields and columns. As such, it makes more sense to use a dynamic database, since it allows for easier modification in the future. Non-relational database handle this much better than relational databases. In conclusion, we feel that non-relational database is more suited for this type of data as compared to relational databases. And with that, we come to the end of our presentation. Thank you.